That's it's an equation. I see some black writing on the board. What is that? Something that isn't written on the wall in my kitchen. Yes, I understand those are all technically correct, but what is that?
Is that like the derivative?
There's a derivative in there, right? Uh-huh. Okay, if I just gave you this, what would that represent? Come on, really? So you're traveling along, and there's a function f of x, right? And there's some x equal a value, right?
Yeah. Oh, this is
what is it?
Distance.
What is this?
Oh, it's a slope.
What is that point right there? A comma what? F of a, right? That's a comma f of a, right? Oh, okay. Okay. Does it help if I subtract it? What about this? I'm going to change one thing. What is that? It's the same thing. I'm just rewriting it. What is it?
It's like distance from one. Oh, that's like derivative. Oh, wait.
What is it?
That's a equation for large number.
I'll give you a hint. What's that the equation? What type of equation is that right there?
Derivative.
Linear.
That's a linear equation, right? So what is this? It's the tangent line, kids. This is the equation of the tangent line right here. This is the tangent line. What this is saying is for values close to the point of tangency, for values close here, the function itself is close in value to the values of the tangent line. The closer you are, like in this neighborhood, that's actually a word in math. I know that sounds weird because it's subjective. In the neighborhood of A, this function approximates that function. Are you with me so far? So around it, it's pretty good. Are lines a little limiting though? Yes, because lines go in a direction, they stay going in that direction. So generally speaking, as you go further and further out, what happens to the accuracy? What? The accuracy gets worse. You can use subjective worse. I can understand. The accuracy gets worse. The accuracy gets worse. So theoretically, if we wanted to have a function, if we wanted to come up with a better estimation, this one is good for just this neighborhood. If we wanted to make it be better for longer, we have to use something other than a line. What's one step up from a line? A parabola, quadratic, right? And then we might be able to get it to be a little bit better, but still, a parabola either goes all the way up or like this, right? So the parabola is probably, the parabola of best tangent parabola at this point would work for probably a larger neighborhood, right? But the thing is, parabolas only go up, right? So the thing is, the parabola is going to go up. Is that going to estimate it well for the entirety of the domain? No, not really. So if you wanted to be even more accurate, you might want to use a cubic or a fourth degree or a fifth degree polynomial. The point is, we can use really long polynomials to estimate functions that are super nasty. There are functions that we have a really, really hard time dealing with. So this is what we're going to do with them. We're going to spike them on the ground and break them apart into a million little pieces. And those little pieces are going to be a sequence that we're going to add together. And it's going to expand out into this big thing. But here's the point. Each of those little pieces we can deal with really quickly. There are functions that you just can't deal with otherwise. You just can't deal with. You look at them and they're elegant and they're sexy and they're awesome. But you literally can't break them apart. You literally can't break them apart. There's no foothold. But you break them into a million little pieces, or an infinite number of pieces, and you can suddenly work with them. It's really, really, really fun. So let's do this on a purely practical level. Let's do this on a purely practical level. Here's that's the associated diagram with the equation I just gave you. Associated diagram. Exciting, very exciting. So what we're going to do now is let's use this one right here. Find the quadratic approximation of cosine near x equals 0. What does cosine look like? Where does it cross the y-axis?
1.
It crosses at what? 1, right? So let's say 1 is right up. I'll put little arrows up here, right? Okay. The axes are going out. So let's say 1 is up here, right? And here's cosine, right? It goes down, and then what does it do? It goes up, and it goes up, and it oscillates infinitely, right? The point we're trying to do is, well, if we wanted the line of tangency, what's the linear approximation right here? What's that linear approximation going to be? Yeah.
Y equals 1.
Exactly. So y equals 1 is your linear approximation. Y equals 1. Why is that the proper linear approximation? It goes through that point, and it has the same derivative. They share derivatives. What's the derivative of cosine at 0? 0. What's the derivative of any horizontal line? 0. So it shares the same, what's the degree? It shares the same first derivative, and it goes through the point. What we're looking for now is a quadratic of best fit. So what's that quadratic roughly going to look like? You know, something like, is it going to face up or down?
Down.
So we're looking for a quadratic that might look something like this. So if this is cosine of x, so g of x is cosine of x, like that. Let's call this green one here some quadratic. We'll call it h of x. What has to be true about h of x, and this is a quadratic? What are they going to share? What's one thing they're going to share? You know that cosine of 0 has to equal what? H of 0. We know that has to be true. What else has to be true? Cosine prime at 0 has to be the same thing at h prime of 0. And we're going to go one further because we now have a higher degree. We had these two things satisfied this one, right? But now we're going up one degree. So what else do we have to satisfy? Has to equal h double prime of 0. So this is where you need to generalize a quadratic, and you can use, the book likes to use C1, C2, and C3. I like to use A, B, and C because it's just how you usually see them first. So let's do that. Let's say h of x is equal to ax squared plus bx plus c. What's h prime of x? 2ax plus b. What's h double prime of x? 2a. So if we use that information right there, if we use that information, these have to be true. H of 0, what's h of 0 going to be? C. H of 0 is c, right? We haven't paired it up yet. We haven't paired it yet. We will. We will definitely pair it. What's h prime of 0? B. And what's h double prime of 0? Nope. 2a. Is everybody with me so far? When you plug in 0, well, there is no x in there anymore, right? It's just 2a. Is everybody with me? So what are we going to pair that with? Well, what is cosine of 0? I know, but what is cosine of 0? 1. Thank you. What's cosine prime at 0? 0. And this is where you have to do a little bit in your head. What's cosine second derivative at 0? Yeah, what's the derivative of cosine? Negative sign, derivative of negative sign is negative cosine of 0 is negative 1. Are you with me so far? That's cosine. Exciting. And then, theoretically, what should we see? Ooh, pretty cool. Pretty neat. That's neat. Okay, it's kind of cool. So we now have, I mean, in this area, in this neighborhood, and again, neighborhood is a real math word. I know it sounds really strange. In the neighborhood around x equals 0, is that a pretty good approximation? Yeah, it's actually a really cool approximation. It's nice. So theoretically, like if we wanted to, visualize. Oh, that really didn't help. I'm sorry about that. Let me get rid of this. Cut. There we go. That right there. It looks like the neighborhood. Like maybe from there to there, it's pretty good, right? It's pretty good. Now, if I wanted to make it more accurate for a larger radius, what would I need to do?
So a
higher degree, right?
Yeah.
Now, theoretically, this is not that bad of a function to work with, right? At least the derivative of cosine oscillates. Sometimes the derivative runs out, like you get to a constant and then it's 0. But sometimes when you start taking the derivative of, say, like a rational function, what happens? Like if you had a polynomial over a polynomial and you started taking the derivative repeatedly, what happens? It gets terrible fast, right? Low d high minus high d low over low squared again and again and again goes boom, right? So this kind of approximation is really fun. I think it's fun to do with cyclic functions with regard to their derivatives. It's kind of cool. You can see patterns. It's really nice. So what we've done right here is we've done this. We have done this. What we've found is that the Taylor polynomial, and I'm going to tell you what that is, the Taylor polynomial of degree 2 approximating f of x for x near 0 is approximately f of 0 plus f prime of 0, f prime evaluated at 0x, f double prime of 0 over 2x squared. How could you figure this out if you wanted to? You would generalize the work we just did. Instead of saying cosine, what would you say? You would just say g of x instead. And if you do this out, when you repeatedly do the derivative of a higher degree function, so for example, where did that 2 come from? Well, when you take the derivative of ax squared, what drops to the front? The 2. If it was a cube, if this was a cubic function, we would also be doing h triple prime, right? If it was a cubic, you would have dropped a 3, and then you would have dropped a 2. That's where these factorials are going to come from. You can look up the generalization in your book. The algebra is something you can look up in your book. I'm not going to do it right now. But what this is right here is the general form for the quadratic approximation. So if you have a function, any function, and you can find the first derivative and the second derivative and evaluate it at 0, you can come up with a quadratic approximation for that function around 0. Around 0. Now, are we going to move it other places? Absolutely. The nicest place to deal with generally is at 0. Generally. Not always, generally. This is the Taylor polynomial of degree n approximating f of x for x near 0. This is the nth degree Taylor polynomial. It goes all the way to n. You see the factorials? What's nice is that there's a great corollary. Hey, third derivative is 3 factorial. Fourth derivative is 4 factorial. The nth derivative over n factorial. It's really about as straightforward. Now this looks ugly, right? In the way that maybe the first time you saw the polynomial general expression, you're like, oh my god, the polynomial general expression. Well, it's relatively straightforward. It's relatively straightforward. But I have to emphasize this over and over again. This right here is super, super, super important. You will absolutely get asked questions on the AP exam specifically regarding this coefficient. Absolutely, absolutely, absolutely. Super, super important. So let's take a look at what it says right below there. Construct the Taylor polynomial of degree 7, approximating the function f of x equals sine x for x near 0. Please do that first one right now. Try that by yourself right now. See if you can do that using what you see on the board right now, right there. The really important takeaway here, do I put them down here? Let me see if I put it at the end here. There are certain Taylor expansions that you're going to have to memorize. There are certain Taylor expansions that you're going to have to memorize. One of them is, indeed, cosine x. So that gives you a strong hint as to which ones you have to memorize. Cosine x is one of them you have to memorize. Anybody can guess one other one? Sine. That's 2 of them. Let's just start with those 2. We're not going to do the sine right now, but can you do sine a very similar way? If that's what cosine is, you want to take a guess as to what sine is? Take a guess. Really directly, everybody. You ready? You just showed me this. You showed me something really cool. You just showed me 1 over 1 minus x is equal to what? 1 plus? What did you just show me? Or is it 0? What is it?
1.
It's 1 plus x x cubed plus x to the 4th plus x to the 5th. Yeah, pretty cool, huh? You've kind of seen something like that before.